Ratios and proportionality is a topic that constantly comes up in physics, so I thought it would be worth making a video about the various types of relationship we can have and how to work with them. We'll start off by talking in general terms about a proportional relationship. That states that y is proportional to x. In that case, that means that y is equal to some constant k times by x. And also, we can calculate that constant k is equal to y divided by x. And that constant value will hold for whatever our values of y and x are. So that means that it will equal y1 over x1, so y1 and x1 are the corresponding values of x and y. And also y2 and x2. So if I had a pair of variables that were directly proportional and I have an initial set of data and a final set of data, then I can use this to relate those sets of data together. That's a directly proportional relationship. You can have an inversely proportional relationship as well. If I do that here, y is proportional to 1 over x. We can apply a similar methodology here. This means that y is equal to a constant divided by x, or a constant multiplied by 1 over x, which is the same thing. And then the constant now is x times y, and that would be true if it's x1, y1, or x2, y2. And that would be the part that we're, or the relationship that we'd be seeking to use. So directly proportional, inversely proportional. From there you can have a direct square proportionality and an inverse square proportionality. In those cases, they're just special cases of those two relationships. So we'll jump straight in now with some physics examples of direct and inverse proportionality. Fick's law, the force applied is directly proportional to the extension. Okay, that's our direct proportional relationship for a spring, and this tells me that I can say that F1 over x1 is equal to F2 over x2. So I can use that and I can solve that with some data. So let's say I have a spring, and for a force of 10 newtons, I get an extension, x1, of 2.5 centimetres. So for that force I get that extension. I then apply force 2, another force, 25 newtons. And I want to know what extension do I get for that force. I want to solve for x2. And so if I rearrange this for x2, multiply by x2, multiply by x1, divide by f1. So this will be equal to x1 f2 over f1. So what you see here is that I'm solving for an extension value here, and in my equation I have an extension on the right hand side multiplied by a ratio of forces. And whenever you use these relationships correctly, that will always be the case. That for the quantity you're trying to solve, the equation will include the same type of quantity, so an extension, multiplied by a ratio of the other quantity, so those two values there. So this is equal to then 2.5 multiplied by f2, 25 over 10, so it's 2.5 times 2.5, which equals 6.32 2SF. You'll notice that I didn't convert this into meters. I don't need to do that in this case because I'm just dealing with this ratio of forces. So my answer I know will come out in centimetres, but you mustn't think that it comes out in meters. It comes out in whatever unit you use, a unit and prefix. So 6.3 centimetres. That's an example of direct proportionality. Let's get rid of this and do an example for inverse proportionality. We'll use R is proportional to 1 over the area. That's resistance for a piece of material is inversely proportional to the cross-sectional area. Here we can use this relationship because it's inverse proportionality. Just by following the same steps if you wanted to work out all of the steps. So that's the relationship we're using. And we want to work out what the resistance is for a piece of material with a larger cross-sectional area in this case. So if the resistance initially is 75 ohms for a cross-sectional area of 10 millimeters squared, you'll notice I'll be doing the same thing. I won't be converting that because for the second piece of material has a cross-sectional area of 13 millimeters squared, so what's the resistance now? So we want to find out what R2 is. R2 here, so I'll divide by A2. So R2 is equal to R1 multiplied by A1 over A2. So we get 75 times by A1, 10 over 13. You can see this will reduce the size of the resistance, which is what we expect if we increase the cross-sectional area. That is equal to 58 T2SF. So that's how we'd work with an inversely proportional relationship. I'm probably writing down more information than you would need to, but it's making the method clear with these steps at least. Here, because here you're just substituting in the values. Now we'll do one of those special cases. This is a direct square. And for this, from waves, we have this relationship. The intensity is proportional to the amplitude squared. Here, we'll come up with an equation like this. Which, as you can see, is the same as the direct proportional relationship, except the x quantity, which is amplitude here, has been squared. I'm going to do two different problems here. The first one, let's find out what I2 might be in terms of the initial intensity. Okay, so that's initial intensity, which is I1 in that equation. So we just want to find out what's the factor that you multiply the initial intensity by to get I2. And what's happening is we have an amplitude, then we put something between the wave source and the detector, and that reduces the amplitude of the wave as it travels through the barrier. So A1 is given to us in the question as 2 micrometers. A2 is 3 micrometers. Now, same prefix, so no need to do any conversions. If one was in millimeters and one was in micrometers, then we would need to convert them, but no need in this case. Right, we want to find out what I2 is, so I2 is equal to I1 multiplied by A2 over A1. Now those both squared, so we can make that a little more simple. It's A2 over A1. All squared there. Now put values in, so we've got, now I1 is just I, so we'll just leave it as I. Multiplied by A2 is 3, I'm just going to leave out the prefix because they would cancel out anyway. And A1 is 2. It's all squared, so that's equal to I times 2.25. And that's the factor that we've stated as our answer. It's 2.25 times the initial intensity. That's the first case we'll use for this relationship. The second one is to, if I write this up here, we don't need so much space. We need to find a ratio of the amplitude. We need to find the final amplitude over the initial amplitude. So that's A2 over A1. Okay, so if we use our relationship here, we've got I1 over A1 squared equals I2 over A2 squared. If I multiply by the A2 and divide by the I1, then I get this, A2 over A1. Similarly as here, it's just all squared, that ratio. It's equal to I2 over I1. Now this is what I'm interested in finding, this exact ratio. So I can use this to find the ratio directly. I just need to square root both sides. So I get A2 over A1 is equal to I2 over I1, all square rooted. The thing we were given in the question, and it's just one thing, was that the intensity is reduced to 1 over 9 of the initial value. So if the intensity is reduced to 1/9, then I2 is equal to I1 divided by 9, and I can put that in here, so I'll get I1 over 9 times I1 all square rooted, so that's equal to the square root of 1/9, which is equal to 0.33. So that's the ratio there, just using the ratio of intensities, or what the final intensity is in terms of the initial. That's two examples then, using this direct square relationship here. Direct square proportionality. See how that? Now we'll do the opposite of that, an inverse square. There's quite a few of these in physics, so it's worth knowing. For this relationship, we will use another waves relationship. I is proportional to 1 over d squared, 1 over the distance squared. This means, just like here, except our x or our y is squared, I1 d1 squared is equal to I2 d2 squared. I prefer to, particularly using these inverse squares, I prefer to use this method. May mean more writing, but often it's much more thorough, so I prefer this, less likely to make mistakes. Right, in the question I need to find I2, so I need to find what happens to the intensity if I1 is 1400 watts per square metre, so that's the intensity of sunlight out of the Earth's atmosphere, quite high up in the Earth's atmosphere. The distance is 1.5 times 10 to the 11. That's about the distance from Earth to the Sun. And D2, this is Sun to Neptune. 4.5 times 10 to the 12 meters. So what's the intensity at Neptune if it's that far away, and that's the data throughout the Earth? We need to find out what D2 is, I2 is. So we'll rearrange that. I2 is equal to I1 multiplied by D1 over D2. That's all squared. So we put the values in now. 1400 multiplied by D1, which is 1.5 times 10 to 11 over 4.5 times 10 to the 12th. That one needs to be squared, and that will come out as 1.56 watts per square metre, and that's how you solve it. Very, very quick. Once you get used to using these relationships, it can be pretty quick. When you're putting in these indices, don't forget to use the times 10 to the x button or the EXP button on your calculator. Often people make mistakes when they're times and 10, then use the XY button. That can lead to mistakes, so make sure you use those buttons. That's what they're there for specifically. Last thing I wanted to say was that it is possible to combine relationships to form new proportional relationships based on some that you know. If I is proportional to a squared and I is also proportional to 1 over d squared, then 1 over d squared is proportional to a squared, and 1 over d is proportional to the amplitude. So you can combine your relationships in that way. And another one that we do in AS physics is resistance is proportional to the length of material you have, and resistance is proportional, inversely proportional to 1 over the cross-sectional area squared, 1 over the cross-sectional area. So therefore, resistance is proportional to length over the cross-sectional area, and as you'll know, that's the basis of the resistivity equation. So that's proportionality and ratios. Hopefully that's helpful. These relationships come up all the time, particularly in Newtonian world gas laws, so it's well worth being able to work with them effectively.